everyone, welcome to iTTV. Today we'll look at also rate of reaction, but today's title will be using collision theory to explain the factors that cause the change in a rate of reaction. So we'll look at how to use the collision theory to explain factors that cause a change in the rate of reaction. So in the previous lesson, we looked at 5 factors that could affect the rate of reaction. Firstly would be total surface area, concentration, pressure, temperature, and the presence of a catalyst that could affect the rate of a reaction. So now we'll look at how we can use this theory to explain how all these 5 factors could either increase or decrease the rate of a particular reaction. Now, firstly, with the fact of total surface area. And for example, in this picture, you can notice that the marble chips are large, and powdered marble, they will actually have higher total surface area. Because we know that the bigger the size of a reactant, the smaller the total surface area. The smaller the total surface area, the lower the rate of reaction. Moving on, if the solid reactant is broken into smaller pieces, the total surface area of the reactant exposed for the reaction is larger. The frequency of collision between the particles increases. The frequency of effective collisions increases, or we could say collisions with energy greater than the activation energy increases. Thereby, the rate of reaction increases. This means that if we want the rate of the reaction to increase, we need to increase the total surface area of the reactant. How do we increase the total surface area of reactant? If we were to break the reactant into smaller pieces. For example, here we have big pieces of charcoal, and big piece of charcoal means low surface area, small surface area. But if we break the charcoal into smaller, finer pieces, this would mean that the total surface area would increase, would be bigger, and thereby the rate of reaction would increase. That's why cooking food with smaller pieces of charcoal would actually cook the food faster as compared to using larger pieces of charcoal. So this shows how the effects of total surface area can affect the rate of reaction. And we looked at how collision theory can be used to explain how surface area affects the rate of reaction. Moving on, let's look at the effect of the second factor, which would be concentration. When the concentration increases, the number of reactant particles per unit volume increases. Thereby, the frequency of collision between the particles increases, and the frequency of effective collision increases. Or, collisions with energy greater than activation energy increases, henceforth the rate of reaction increases. Now, this means that if we increase the concentration of the reactant particles, we can increase the rate of reaction. A very straightforward analogy, because when we increase the concentration of reactants, we're actually increasing the number of reactant particles per unit volume, as in how many particles per milliliter. The number of particles per cm cube has increased if we increase the concentration, because the particles will collide more, and if you have more collisions, that would be higher percentage of effective collisions, provided the particles are in the correct orientation, and secondly, provided that the collisions have energy greater than activation energy. Then only effective collisions will happen. So that was how we can use collision theory to explain how concentration affects the rate of reaction. So let's look at the third factor, pressure. At low pressure, if you look at the picture on the slide, the particles, reactant particles, are very widely spaced from each other. They're a bit far apart at low pressure because the number of particles per unit volume is smaller. But we look at the second picture on the right, that at high pressure, the volume is smaller and there would be a greater number of reactant particles per unit volume, which means for every milliliter or for every cm cube of volume, there would be more particles at high pressure. So how do we use collision theory to explain the effects of pressure on the rate of reaction? If you look at me with the slide, when the pressure increases, the number of reactant particles per unit volume increases. So the frequency of collision between the particles increases, thereby the frequency of effective collision increases. Or collisions with energy greater than activation energy increases, henceforth the rate of reaction increases. As explained earlier on, with higher pressure, there will be more reactant particles per unit volume. So you have more particles, they will collide more, and there will be higher probability of effective collisions, and therefore the rate of reaction increases. Let's look at the fourth factor, which would be temperature. How can we use collision theory to explain how temperature influences the rate of reaction? So, if we look at the slide, when temperature increases, the kinetic energy of the particles increases. The frequency of collision between the particles increases. Again, the frequency of effective collisions increases. Therefore, collisions with energy greater than activation energy increases, and the rate of reaction increases as well. So what does this tell us? This tells us that with higher temperature, there will be more collisions between reactant particles. Why is that so? Because we know that when we provide energy to reactant particles, they will absorb this energy and they will move faster, they will collide with each other faster. So the frequency of effective collisions would thereby also increase, henceforth increasing the rate of reaction. And we look at the last and the fifth factor, which was the effect of a catalyst. Now, if you look at the slide, there is an energy profile diagram to represent the exothermic and endothermic reaction. EA is activation energy without catalyst. EA apostrophe is activation energy with catalyst. To further understand how the energy profile is different with and without catalyst, let's look at the board to have a deeper understanding. Okay, so I'll draw the energy profile diagram for exothermic reaction first. This is energy versus reaction pathway. A typical energy profile diagram to represent exothermic reaction pathway would show that the reactants are at a higher energy level than the products. So something like that, whereby the reactants, they are at a higher energy level than the products. Now, what we are concerned of is the activation energy. This is activation energy without a catalyst, okay? So this first is EA without a catalyst, whereas EA with an apostrophe on top is the activation energy with a catalyst. So we'll look at how the activation energy will be like without a catalyst. And this will be the activation energy needed without a catalyst. How about the activation energy with the presence of a catalyst? I'll use a blue chalk to show the difference. Okay, so with the catalyst, the activation energy level is much lesser. So in blue will be EA prime. What you can observe from this would be that the activation energy level would be lesser if the reaction proceeds in the presence of a catalyst. But if there is no catalyst, the amount of energy needed by the reactants to become products will be so much more as compared to if the reactants have catalyst in the experiment. So this activation energy is much lower in the presence of a catalyst. Now, how would the energy profile diagram look like for an endothermic reaction? So let's look at the board by drawing two profiles side by side so that you can see the difference. So I'll draw a partition. Okay. So this is for an endothermic reaction. Same axis, that would be energy versus reaction pathway. Remember, the difference between an endothermic and an exothermic reaction will be the difference in the energy level of the reactants and the products. For an endothermic reaction, the reactants are at a lower energy level than the products. So the energy profile diagram for an endothermic reaction looks something like this, whereby the reactants are at a lower energy level than the products. So using the same abbreviations, EA, EA prime, let's see how the activation energy will be like without a catalyst. So as a guide to help you remember, it's always from reactants all the way to the top of the peak. So this here will be EA. This is the minimum energy required by the reactants to become products. Now, how would the activation energy level be in the presence of a catalyst? So perhaps I'll use a blue chalk again to show the difference. As you can see, the activation energy is lowered in the presence of a catalyst. So a curve like that would show that the activation energy level is lesser. This will be EA prime. As illustrated in this energy profile diagram for the endothermic reaction, without a catalyst, the activation energy level is so much. The reactant particles need to have so much activation energy before they become products, before a reaction takes place. But in the presence of a catalyst, the reactants need lesser amount of activation energy before they become products. So what we can conclude from these two energy profile diagrams would be that the presence of a catalyst increases the rate of reaction. But remember, catalysts do not increase the amount of product that we can get at the end of the experiment. So, let us see how we can use collision theory to explain how a catalyst affects the rate of reaction. positive catalyst lowers the activation energy. The frequency of effective collisions increases, or we could say the collisions with energy greater than activation energy increases, thereby the rate of reaction increases. So, to help you understand, does a catalyst increase the frequency of collisions between the particles? And the answer is no. Catalyst only increases the frequency of effective collisions. Remember, a catalyst does not increase the frequency of collisions, but they only increase the frequency of effective collisions. And a catalyst do not increase the final amount of product at the end of the experiment. Positive catalyst increases the rate of reaction by lowering the activation energy. So, what are some applications of these factors that affect the rate of reaction? Here are some examples. In daily life, by using smaller pieces of charcoal, storing food in a refrigerator, cooking food in a pressure cooker, and cutting meat into smaller pieces before cooking. So let's look at this simple example. When we have large piece of charcoal, total surface area is low, rate of reaction would also be low. But when we cut up the charcoal into smaller pieces means bigger total surface area. Bigger total surface area means higher rate of reaction. So this means that food can cook faster. Meat and barbecue can actually cook faster using smaller pieces of charcoal compared to large pieces of charcoal with smaller surface area. If we store food in the refrigerator, basically the temperature of the food in the refrigerator is low. And low temperature means low rate of reaction for the bacteria and the fungus to spoil the food. We don't want our food to be spoiled. So if we keep our food in the fridge with these low temperatures, it can actually slow down the rate of food decomposition by bacteria, by fungus, by protozoa. Thirdly, if we cook food in a pressure cooker, because a pressure cooker uses high pressure to cook the food. So we learned just now that the higher the pressure, the higher the rate of reaction. So when we cook food in a pressure cooker, we're actually accelerating the rate that the food is being cooked. And with the last example, similar to using smaller pieces of charcoal, if we cut our meat into smaller pieces means bigger total surface area. And bigger total surface area means higher rate of reaction. So if we want our pieces of meat or fish or pork to fry faster, to cook faster, we just cut them into smaller pieces. That would increase the rate at which it is being cooked. Moving on, let's look at the usage of catalysts in the industry. So we have finished looking at how to use collision theory to explain how these factors can affect the rate of reaction. And we looked at specific examples. So now we move on to something different. We'll look at 3 specific examples how catalysts are used in today's chemical industrial processes to increase the rate of reaction. And all these 3 examples are positive catalysts. Let's look at the slide for the first example. In the Haber process, it is to manufacture ammonia. As you can see from the equation, gaseous nitrogen reacts with gaseous hydrogen to produce ammonia gas. And the catalyst for this reaction would be finely divided iron powder. So we not only use a positive catalyst, which is iron, to speed up the reaction, but we also try to increase the total surface area of the catalyst by using finely divided powder. as compared to using large chunks of iron metal to increase the rate of production of ammonia. Let's look at the second example. The second industrial process would be the contact process. This is to manufacture sulfuric acid. The key reaction in this contact process will be when gaseous sulfur dioxide reacts with oxygen to produce sulfur trioxide. And the positive catalyst being used will be vanadium oxide. Some books will say vanadium pentoxide as well. So this is another example of how positive catalysts can accelerate a reaction. Let's come to the final example, will be the Ostwald process. In the Ostwald process, it's to manufacture nitric acid. The key reaction pathway here will be when ammonia gas reacts with atmospheric oxygen to produce nitric oxide. And in this case here, the catalyst will be platinum. So those were three specific examples in how the use of a positive catalyst will increase the rate of reaction. So we looked at how we could use collision theory to explain how all these 5 factors could affect the rate of reaction. We looked at how the effect of concentration, pressure, temperature, total surface area and a catalyst could affect the rate of reaction. And then we looked at how a positive catalyst can be used to increase the rate of reaction for 3 processes, which would be the Haber process, contact process and Ostwald process. So with that sums up our lesson for today. Thank you very much for watching iTTV. We look forward to seeing you all again next time. Thank you and have a great day.